In propositional logic, if we have a clause containing a literal phi and another clause containing a literal not phi, we can use propositional resolution to derive a new clause by collecting together the literals from both clauses except for the complementary pair of literals. Relational resolution is similar, except the positive literal and the target of the negative literal do not need to be identical. It suffices that they are unifiable. A slightly simplified version of this rule is shown here. Given a clause with a literal phi and a second clause with a literal not psi, such that phi and psi have a most general unifier sigma, we can derive a new clause by collecting together the remaining literals from each clause and applying sigma to that result. Okay, here's an example. Suppose we have a clause containing the literal p of ay and another clause containing the literal not p of xb. We can unify p of ay and p of xb with a most general unifier x gets a, y gets b. Hence we can resolve these two clauses. We form a new clause consisting of the remaining literals from each of the original clauses, in this case r of y and s of x. We apply our most general unifier to this clause, and thereby we produce their resolvent, namely the clause consisting of the literals r of b and s of a. We'll see in a moment how we can use resolution to solve some really interesting problems. But first, we need to refine our definition of the rule to deal with a couple of shortcomings. Okay, consider the two clauses shown here. Given the meaning of these clauses, it should be possible to resolve them to produce the empty clause. However, the two atomic sentences, as stated, do not unify. The variable x must be bound to a and b at the same time, and that can't be. Fortunately, easy fix. All we have to do is to extend the resolution principle slightly, as shown here. Before trying to resolve two clauses, we select one of the clauses and rename any of the variables in that clause that happen to appear in the other clause. Renaming solves the problem in the case we just saw. We simply change the variables in one of our clauses before attempting to resolve them. After renaming, we see that the positive literal and the target of the negative literal can be unified, as they can be resolved, in this case leading to the empty clause. Oops, not quite done. There's still one more little thing we need to worry about. As stated, even with variable renaming, the rule's not quite good enough. Given the clauses shown here, we should be able to infer the empty clause. However, it's not possible with the preceding definition, even if we rename the variables. Clauses can be resolved in various ways, but the result is never an empty clause. Okay, we can fix that with the notion of factors. A subset of literals in a clause capital phi has a most general unifier gamma, then the clause obtained by applying gamma to phi is called a factor of phi. For example, literals p of x and p of f of y have a most general unifier x gets f of y. So the clause p of f of y, r of f of y, y is a factor of p of x, p of f of y, r of x, y. Note that also any clause is trivially a factor of itself. So this clause has two factors, the original and this somewhat reduced clause. Okay, now using the notion of factors, we can give our complete, final, ultimate definition for the resolution principle. Suppose that a clause, capital phi, and another clause, capital psi, are in our proof. If there's a literal little phi in some factor of capital phi after renaming, and if there's a literal not little psi in some factor of capital psi, such that little phi and little psi have a most general unifier, then we can form a resolvent of these two clauses as shown here. Okay, let's see an example. Using this enhanced notion of resolution, in fact, we can solve the problem we saw just a couple of slides back. Consider the premise P of x, P of y, and all the other premise not P of u, not P of v. The first premise has a factor P of x, and the second has a factor not P of u. And these two factors resolve to the empty clause in a single step. One little consideration here is that we cannot actually replace a clause by its factors. We actually have to retain the original clauses as well, which is, of course, they are factors too. The example here shows what goes wrong if we try to replace a clause by its factor and eliminate the original clause. All right, the first three clauses, premises in this case, in the top derivation, lead to the empty clause after just 2 steps of resolution. Okay, now, by contrast, consider the partial derivation shown at the bottom. Start with the same 3 clauses. Clause on line 4 is a factor of the clause on line 1. Suppose we were to discard the clause on line 1 and replace it with this factor. Problem is that we would then be stuck. There would be no further resolutions we could perform using just the clauses on lines 2, 3, and 4. So the upshot of this is that factoring is useful. It allows us to derive conclusions we would not otherwise be able to produce. However, we must consider resolutions with the unfactored clauses as well if we want to be sure to produce all possible conclusions. Okay, that's it for our treatment of relational resolution rule. Now it's time to put it to work, solving some logic problems. It turns out there's quite a bit we can do with it.